A very good afternoon to one and all. Welcome back to third session in the day one of 5-day national workshop on advancements in antenna engineering using artificial intelligence. We have an eminent resource person, Dr. Chinmoy Saha, with us. Dr. Chinmoy Saha received his BTech, MTech, and PhD degrees in Radio Physics and Electronics, University of Kolkata, India, in 2002, 2005, and 2012, respectively. He is currently working as an associate professor in the Department of Avionics, Indian Institute of Space Science and Technology, Department of Space, Government of India. He has visited several international universities of repute like Royal Military College of Canada, Queen's University, Canada, during 2015 to 2018 in various capacities and having collaborative research with RMC Canada, Kingston, Ontario, and University of Alberta, Edmonton, Canada. He is a senior member of the IEEE and a life member of IETE. He is the founding and current chairman of IEEE MTTS Kerala chapter. He has served as the chairman of Antennas and Propagation Chapter of IEEE Kerala section during 2018 to 2019. Dr. Saha has received several prestigious awards, which includes Outstanding Teacher Award in 2019 from the Department of Avionics IIST, National Scholarship from Ministry of Human Resource Development from Government of India, Outstanding Contribution Award from the APP-MTT Kolkata Chapter, Best Contribution Award for the notable services and significant contributions towards the advancements of IEEE and the engineering profession from IEEE Kolkata section, and several Best Paper Awards in various international conferences. His current research interest includes wireless power transfer and energy harvesting, channel modeling for WB and UWB systems, microwave circuits, engineered materials, metamaterials inspired antennas and circuits, reconfigurable antennas, and multifunctional antennas for modern wireless applications, dielectric resonator antennas, and terahertz antennas. He has more than 120 publications in peer-reviewed national. Am I audible? Is it audible? Dr. Saha?
Yes, I can hear you. I can hear you.
Okay, thank you, sir. Dr. Saha has more than 120 publications in peer-reviewed national and international journals and conference proceedings, and authored 2 books with Cambridge University Press UK and Taylor and Francis USA. The book link is posted in the chat box for your reference. Dr. Saha is on the board of reviewers of several international journals of repute, including IEEE Transaction in Microwave Theory and Techniques, IEEE Transaction in Antennas and Propagation, IEEE Antennas and Wireless Propagation Letter, IET Microwaves, Antennas and Propagation, Electronic Letters, Nature Scientific Reports, etc. He is an associate editor in IEEE Access and International Journal of RF and Microwave Computer Aided Engineering, Wiley, and guest editor-in-chief for a special issue in the same journal. I request Dr. Chinmoy Saha to take over the session. Over to you, sir.
Yeah. First of all, a very good afternoon to all of you. I believe you had a good lunch, but I also hope you are not feeling sleepy as an outcome of that good lunch, right? That is a possibility, especially in physical conferences and workshops, because normally in India we offer a very good lunch with a lot of items and all, and then the next speakers is at advantage, like he has to speak less because people are sleepy, and sometimes it is advantage for some of the serious speakers. Anyway, so let me first extend very sincere thanks to the organizers, especially Dr. Guptirani, whom I have probably met quite a few times at NIT Trichy in connection with some events which was organized by a group under the guidance of Professor Raghavan and then other professors like Professor Karthikeyan. And I know and I believe that even though it's a virtual event, it also requires quite a bit of preparation. So, with the sincere thanks to the organizers, led by Professor Vikrani and all other co-organizers, coordinators for this particular event, and sincere thanks to this initiative of AICT, ATAL initiative. Let me go to my presentation. Once again, sincere thanks to everyone, especially during this COVID pandemic and post lockdown time, because the civilization is facing a lot of challenges, a lot of difficulties on different fronts. At least academic part, experimental part, research part is not disturbed because of this kind of initiative, which is taken by academicians like you. Like as you know, different institutes and universities are taking, organizing classes in virtual podium. Similarly, this kind of initiative, workshop, conferences, faculty development program is a very good initiative to ensure that the learning chain is maintained, right? So with this, let me go to my presentation and go to the agenda. Like what I am going to talk on is, as you know, as the title suggests, I'll be talking on the antennas for cognitive radio and 5G applications. Let me know when you see my screen. When you see my screen,
Yes, sir. It is visible, sir.
yeah. So sometimes there is some delay of 4 to 5 seconds, uh, depending on the user's data connectivity. So that's why uh, you make sure that what I am talking and what I am showing are synchronous. So I'll be probably try to adjust accordingly. So this is the agenda, like antennas for cognitive radio and 5G applications. This is the main agenda for this particular talk. Because when I was contacted by Dr. Vikrani, she mentioned that it's a uh, online and it's a 3 hour event for us. So I thought like in 3 hours I can cover quite a bit amount, starting from the journey that we have started around 2006. So I'll be going to like those virtual journeys, and I'll show you the works related to some of the antennas that we have developed for versatile applications. As I do normally in international podium, let me take a minute to introduce my institute. As you know, the Institute of Space Science and Technology, Trivandrum. We are here at the extreme southern part of India, not very far from the organizers who are at Puducherry. And these institutes started its journey with a specific focus of creating quality human resources for space, Department of Space Initiative. And it's a matter of great pride and privilege to mention that currently almost 1,000 ISRO scientists are graduates of this particular institute. We started our journey in 2007 under the leadership of Dr. Kalam, the the missile man or the race visionary and scientist of India, of course, and then he became the president of India later on. And, this is a panoramic view of our campus, and I invite you, when you get an opportunity, you will visit.
Sir, your voice is not audible, sir.
Sir, please unmute, sir.
Muted throughout, right? How I got muted? Like you couldn't hear me till now?
Yes, sir.
Hello?
Yes, sir. It is audible now.
So, no, I already talked for 4 to 5 minutes. Did you hear anything?
Yes, sir. Just now it went, sir.
Okay, okay. So I did not do anything. So please make sure that you
Yeah.
know nothing is done from some other participants end. And I request everyone to ask only when you are asking the question. Then only you unmute. Otherwise, keep yourself muted throughout. Okay, because background noise will disturb the flow. Fine. I cannot ensure stopping background noise around me, but at least you can ensure that. Right? Okay. So did you hear about when I was talking about the about IST and the map? You could hear me at that time.
Yes, sir.
Okay. So this was the slide probably where accidentally I got muted. So this is the typical research activities that's happening in our group. So as you can see, probably sometimes it takes time in some of the slides to get uploaded. So I'll be a little bit slow. So our activities can be divided into quite a few wings. One is the printed antenna research, where we have designed different kind of antennas for different kind of applications. And these applications that I'm going to talk on today, that cognitive radio and the 5G applications is one of the major applications which is very useful for multiple phones for currently modern wireless applications. And being in IIST and being part of Department of Space, we have very strong collaboration with different space centers, different ISR centers. So one of that is very strong association with uh, National Remote Sensing Center, Hyderabad, for designing antennas for satellite tracking applications. So few of my PhD students and some of the MTech students also are working on that particular type of antennas, which are very specific and very focused antennas for LEO satellite tracking of applications with very high gain and auto tracking capability, so that you ensure that you receive data from the satellite, and at the same time you ensure that the ground station antenna and satellite antennas are looking towards each other. And then we designed some conformal antennas for different other kind of space applications, like reusable launch vehicle applications, which we did with Vikram Sarabhai Space Center. That was a design of very compact and wideband linearly and circularly polarized antennas for RLV type of applications. And the last one, that microwave and millimeter wave, WPT and terahertz systems. Here we are basically trying to do some systems, not only the antennas but systems in general for next generation communication, like millimeter waves and terahertz applications. And then very recently we have started working on wireless power transfer, energy harvesting, and some of my students are also working on optical fiber based nanosensor applications. So this is a few slides I'll be spending in giving more glimpses of towards our activities. So these are some printed antennas. I will be explaining in detail some of the stuff. These are some ultra-wideband antennas for frequency notched and narrowband applications simultaneously. Dual complementary antennas. Some of those are the same antenna can give multiple antenna functionalities, which we have named as dual complementary antenna. And these are some unique articles which you will get in IEEE transactions and IEEE antennas and wireless propagation letters. And these are some glimpses of some of the results indicating the different multiple antenna functionalities, which is output of our prolonged activities for several years. This particular slide, as you can see, that there are two sections. The first section is a collaboration with Vikram Sarabhai Space Center in connection with designing certain kind of antennas for some applications. As I was mentioning earlier, LP and CP type of antennas for these are later on changed to reconfigurable structure in the conformal structure. And the second part is a strong collaboration with National Institute of Interdisciplinary Science and Technology in connection with different kind of dielectric resonators, as you can see probably over here. And these dielectric resonators and these hybrid monopole type of antennas together, when you mix them, you get a very wide band performance. That is one aspect, but at the same time, controlling the bandwidth of the antenna was one of the focus for our application, because in many practical scenarios, along with the desired signal range, you get some undesired noise bands also. So if you really want to have an antenna which will be self-sustained in terms of noise reduction, then this is a very good design, because you can control the bandwidth of the antenna. We reported these results, and as you can see probably from the structure, the same antenna for different combination of this type of loading, which are some metallic sleeves or some kind of metallic being loaded on the antenna, and thereby they can control on some of the resonances of the antenna. And as a result, this antenna becomes a beautiful bandwidth tunable antenna. This is with respect to different kind of work that we have done using metamaterial inspired structures and circuits. Some of this I'll be explaining in very detail today, so let me go a little bit quick over here. Only thing is, these are some of the filter integrated antennas, or filter some people call it. So these are some metamaterial structures people call them, but these are simple splitting resonators which are loaded on a printed line, CPW type of line, and then you can load them on different kind of antennas, Vivaldi antenna, horn antenna, etc. Even for dielectric resonator kind of antennas for different kind of applications. And this is basically a balanced antipodal tapered slot type of antenna, which is basically a planar antenna. To show you the intermediate metallization, these are simply unscrewed, and these are two basically chalks that we use in the classroom in normal situation. So this is a balanced structure which has a very unique advantage of cross-polarized radiation reduction. So this is a BATSA, as I mentioned, balanced antipodal tapered slot antenna for low cross-polarized radiation. And this particular slides explains how the cross-polarized radiation is mitigated using this kind of balanced structure. Basically, the orthogonal component of the electric field which causes the undesired radiation is actually mitigated by this particular kind of arrangement over here. So when I will be talking on many applications in today's long lecture, probably we will be dividing in T and post T, or whatever virtual T probably. So I will be coming into details of these applications. And this is an article with IEEE antenna and transfer cognitive radio. And I'll be explaining this type of antennas, where the antenna is loaded with different kind of switches and different kind of resonators to come up with some new kind of antenna functionality, which we have named as multifunctional antenna. And these antennas are very good applications in terms of the new smart radio, or the software-defined radio, which you call it as a cognitive radio. So I'll be explaining these slides in detail later on. Just to give you a crisp comment on this, that the same antenna, when loaded with different kind of resonators and using a control mechanism, using a motor and some kind of switches, can invoke multiple antenna functionalities. So the same antenna gives you tunable notch function and tunable narrowband function. I'll be explaining this experimental setup in detail very soon, so let me skip this particular part. And this experiment was repeated on various kind of antennas at multiple times during my research time, as well as when some of my students, PhD students, are working on at IIST, and sometimes we have done this experiment at University of Queen's University and University the Royal Military College of Canada during multiple visits that I had over there. And this is not very much related to the today's agenda, but just as I said, I'll take you through a virtual journey of our research group. This is some new kind of work that we have started around late 2017, and we have already progressed in terms of new mechanism. Am I audible? Am I audible?
Sir, you are audible, sir. Participant, please mute your mic.
Can you hear me?
Yes, sir, we can hear you, sir.
Yeah, I can hear some other people also. Okay, so please get muted. Yeah.
Yes, sir, yes,
Yeah.
sir.
So this is dielectric resonator based wireless power transfer, where we have basically one kind of cavity, and that cavity is loaded with different kind of dielectric resonators, and these dielectric resonators are excited by some kind of loop, which is basically, as you know, it's basically a magnetic dipole. It excites certain kind of modes in the dielectric resonator, and the matching of the dielectric resonator mode and this cavity mode, which is a split cavity resonator, together excites three different kind of mechanisms, which are called bonding, anti-bonding, and non-bonding mode. And at the non-bonding mode, we get basically a very high transfer efficiency. So this is for near field wireless power transfer applications, and some of the extensions people are conceiving. We are also in that track, is the powering some of the embedded gadgets, biomedical gadgets, in terms of pacemaker or some kind of hearing aids, etc. You can see a experimental setup over here, and this is the cavity, and these are the pieces of dielectric resonators which are placed inside this, and this is connected to the vector network analyzer, as you can see probably in the screen. So there are three different modes, 1, 2, and 3, and at the intermediate mode you get the maximum power transfer efficiency. Again, this is another strong wing of work, like the photoconductive antennas for terahertz applications. Terahertz, as you know, it has a lot of space applications, not for terrestrial or conventional communication, because terahertz is quite that because of the atmospheric challenges in terms of the high attenuation due to the water vapor, etc. The terahertz signals cannot be used for conventional communication. But when you have a space environment, and there is requirement of huge data transfer and etc. So terahertz is the best. So NASA and some of the European space agencies have started work in this particular direction. ISRO also started work very recently in space application centers in some of the wings of the URL satellite center. So we have started this work of photoconductive antennas, which is a different ball game. Not I am going to discuss today, but probably you have heard me in other forum, like at 400 to 600 gigahertz, we have designed some antennas. Of course, it involves nanoelectronics. Excitation is done by lasers, so you need the solid idea of photonics and conventional antenna engineering. Also, these antennas, because these are realized on semiconductor substrate, you need to have a very solid understanding of the materials in terms of their mobility, magnetic area, lifetime, and so on and so forth. So these are some of the structures that was designed and fabricated. The photoconductive antennas, these are very, very small micron level. You can't even see them in naked eyes, because these are nanometer kind of dimension. But we could realize and fabricate them at Space Application Center, Ahmedabad. And these are some of the typical equipment. This is a kind of bow tie kind of structure. This is a typical dipole antenna, but not a typical one, because it is a photoconductive antenna. Its mechanism is completely different. This particular part I already discussed, that regarding the collaboration we are having with VSCC, and this particular part, second part of the slide, the bottom part, is basically some tri-band monopulse feed type of antenna for auto tracking of LEO satellites receiving data simultaneously. Some of my students are doing very good work on this particular thing. So these are some realized prototype. Now, because the current system at NRS is receiving data only at X band, but in near future, the idea is to receive more data from the satellites, because of so many number of payloads and etc. You know there. So data rate or data transfer rate will be increasing. And as you know, the satellite pass, I mean the time during which satellite and the Earth station antenna can communicate with each other is just few minutes in a day. So during that small pass, you have to receive a lot of data. And then current requirement is to ensure that we receive the data in multiple bands, that is X band, Ka band, and S band. So this is a tri-band antenna under realization, and this is a dual band antenna at S band and X band together receiving the data. This is a very basic mechanism explaining the sum mode, that means kind of directed towards the data, and this is the different mode of the antenna. So in this virtual journey of the research activities in our group, I enter into the presentation. I'll be starting some of the things, because the antennas, cognitive radio antennas and 5G antennas that I'll be talking about has quite a strong inclination and strong correlation with the metamaterial inspired concept. So I'll be spending some 10 minutes to explain some of the briefs of the metamaterial. Probably those who have heard me in other workshop, probably in the month of February, I was there at NIT Tripurapalli for that Indo-Canadian DST Spark workshop. There I talked about in a very detailed manner, but today I'll spend around 5 to 10 minutes to give you the basic ideas. Then I'll be coming to the concept of the cognitive radio antennas and some of the 5G antennas. So this is the first leg of the technical part, the metamaterial inspired concepts. So probably those who have worked and probably working in the metamaterial areas, we call them meta, because it's not available in the nature, but then you can realize them using the artificial engineering, like you can create those bases and lattice, by cascading those bases together in a periodic structure. You can try to give a get a metamaterial which typically people define in terms of the negative mu and negative epsilon or their combination, and this is realized by two different kind of structures getting amalgamated. One is the split ring resonator, which looks like this, and the other structure is basically the thin nanowires kind of structures. So when you place them together, that is a unit cell or basis, and when such unit cell or basis is repeated in 3D, then you basically get a metamaterial kind of structure. You have probably gone through some of the theoretical explanations and some of the experimental verification part also, that such structures, if you do a free space measurement using two pair of horns and you get the S1 measured, then you try to do the material characterization, and from that when you try to retrieve the mu and epsilon, you will see there is a narrow window across which this medium gives you an effective negative mu and negative epsilon, which is a strong function of frequency. And then this is a second approach which was proposed by Professor Callows and Ito in 2002. Even though this approach is more popular, in this group, Professor Callows and Ito is from University of Montreal now, École Polytechnique Montreal. Dr. Callows and Ito together proposed another alternative technique of transmission line based metamaterial. In transmission line based metamaterial, it is basically the idea that in a normal transmission line you will have a series L and a shunt C. But if you can artificially create in the complementary structure, that is, you will have a capacitor in the series R and an inductor and the shunt arm, then such a line will have a composite nature, or I can say a complementary nature. So such a line they named as a meta line. So this is a historical background and chronological development towards that line. 1968, it was the Veselago's dream. He presented this idea in a seminal paper, and then 1996, first John Pendy proposed wire kind of structure. Those who are aware of the classical physics development, you must be knowing that below the plasma frequency, the metal exhibits the the normal and anomalous dispersion. The negative epsilon kind of nature is available. But Pendy proposed this wire structure, and he brought them into the microwave regime, because those frequencies will be in the optical frequency region, which exists in the classical physics. And then in 1999, there was a breakthrough kind of experiment where Pendy first proposed split ring resonators, which is basically a pair of C-shaped structures, placed in a diametrically opposite side of the gap, and then Smith first did an experiment and showed the material characterization and the parameter extraction, and then the rest of the part has been many applications, metamaterial inspired circuits, in planar microwave circuits, and then different kind of power divider, phase shifters, compact antenna, electrically small antennas, etc. started coming. And at that time, no one thought that metamaterial inspired antenna might have so much of applications, because people are mainly thinking of the absorbing applications and some kind of plugging applications, or maximum that electrically small antennas. So this is little bit of more theoretical background, like Drude-Lorentz theory you can apply, and you can show that below the the cutoff frequency, you can see that effectively you have epsilon negative, And this type of structure, which is called the the split chain resonators, which is excited by orthogonal magnetic field or this or gap oriented electric field, you can replace them by an equivalent circuit like this, and using this the Lorentzian plot that is below this frequency, within this particular frequency range, the parameter is effectively negative. I am skipping this theoretical part, and so this is what the fundamentals of metamaterial and double negative material I wanted to show you. So as this picture shows, like this type of electric field which is oriented along the wires gives you a plasma frequency, and below this frequency your epsilon is negative. Whereas this type of structure, when you have orthogonal magnetic field on this, you have a region of frequency where mu is negative. So when you combine these two structures together, like ENG and this is called MNG. So ENG structure and MNG structure, when it's combined and you create a 3D structures like this periodic structure, you really get a region where you get the double negativity in your structure. So this is the a little bit more interesting and physical explanation of this particular metamaterial, which I have defined as a propagation in metamedium. Let us imagine that as a classical electromagnetics engineer, we know that the material's properties are basically defined by mu and epsilon. That's why they are called the constitutive parameters. Sometimes sigma as well, because sigma is the cause of the attenuation and cause of the signal strength to go down. So classically we know that materials will have only mu and epsilon positive. So imagine that such a medium is here and you have another such medium here. But just for sake of understanding, let us imagine that in between I have a medium which is in these blue blocks where I can have an engineered medium. So engineered medium means that medium's property I can control. So if I assume that all four combinations like mu and epsilon both can be positive or negative, then these four combinations will come into picture. So those four combinations can be described in this four particular quadrant. So first quadrant, you will have both mu and epsilon positive. So engineered medium is actually a double positive medium here. And then we can have only mu negative, but epsilon is positive. So we can call it mu negative, that is MNG. Whereas if we come here, then it is called ENG, epsilon negative type of material. And then when we have both mu and epsilon negative, you have double negative material, which is the third quadrant. But what is the implication of this particular diagram that I am showing to you? This particular field diagram that I am showing is very, very interesting to understand the physical significance of presence of an engineered medium between two conventional medium. So block 1 and block 2 are conventional, and intermediate block is actually the engineered medium, which is represented by 4 cases. Now you imagine I have launched a signal over here, and this particular case is actually showing how the whether signal will reach in medium 3 or not. If it reaches, how it reaches, right? So let's try to see that one. This is an animation. I hope it will work. I hope. Yeah, probably it's working. So this is the propagation in double positive medium. So this is a double positive medium. Medium 1 and medium 3 are of course double positive. So I have a signal over here. You can see without any hiccup, the signal is reaching into the medium 3. Okay. So as expected, but if I apply the simple basic physics, so that we know that if one of the constitutive parameters is negative, then beta, which is omega square root of mu epsilon, becomes imaginary. And as you know, if beta becomes imaginary, then that won't, corresponds to the propagation. So that's what is happening over here. When I have a mu negative medium, because I clicked on the second quadrant, you see we have launched the signal over here, and you see the signal effectively doesn't reach into the medium 3. So what's happening in medium 2? Either the medium is getting absorbed or it is getting reflected. So based on this phenomenon, different structures and devices can be realized. So this is a mu negative property. Similarly, if you see the third medium epsilon negative, because here epsilon is negative but mu is positive, As we said, here also the beta will be complex, and probably you expect a similar kind of situation over here. So let's see. So in this case, also, as you can see now, you have launched the signal at the block 1 and you don't get anything in the block 3. That is because of the same kind of interpretation I talked about, right? And the most interesting part is that this third quadrant where we have both mu and epsilon are negative. What happens when both of them are negative? Actually, you will have propagation because now you have beta equal to omega square root of mu epsilon. But here, I mean, I have skipped some of those theory. What we are supposed to see is that phase and group will be opposite. Phase velocity and group velocity will opposite. That means even though the energy will be going from medium 1 to medium 3, the phase of the wave in medium 2 is opposite. So you see the wave reaches from medium 1 to medium 3, but in the second medium, intermediate medium, you see while the energy is going in this direction, that means the pointing vector is going in this direction, but the phase of the wave is moving in the opposite direction. So what is the interpretation of that? That means in a conventional medium, when electromagnetic wave propagates, I have a phase retardation. Phase retardation. That means if the wave travels by lambda by 2, I get a phase difference of 180 degree. If the wave travels by lambda by 4, I get a phase difference of 90 degree. But in this kind of medium, because phase is moving in opposite direction, so phase will be negative. So instead of 180 degree, I will be minus 180 degree, or 90, I will get be minus 90. That means instead of phase retardation, we will be getting phase advancement. So such concepts have been used by many groups to create the zero dispersion line or zero delay line. That means if you have a conventional medium, then you have a phase retardation. If that part is connected or combined with another transmission line, which is a metamaterial type of transmission line, so that will cancel the phase delay that has happened because of the conventional medium. So by cascading them, you can ensure after the signal goes through both the medium, you get actually a zero delay line. So even though this particular part is not very much linked with my presentation, I wanted to show because the structures now I am going to show and I want to discuss in detail has a very strong relationship with this particular physics. So this is a slide probably you have seen in many other forums, many researchers and presenters are showing. So this is basically the outcome of what I showed in the previous slide. So if you have mu and epsilon both positive, you will have forward wave propagation in quadrant 2 or quadrant 4, where you either of the parameters are negative. It is basically no transmission in the second medium. That is, you understand because of the phenomenon that I discussed. Whereas in the third case, you had the reversal of Snell's law also happens because of this double negative metamaterial. So what you see is here you see the wave in the left-handed medium, instead of going in this direction, it is going in this direction because the angle is negative. So it is called the reversal of Snell's law. You can see from here also that in terms of the refracting index, negative refraction. So here what's happening, this is a conventional medium and this is a n2 greater than 0 refracting index. So the wave is going in this particular direction. So these kind of phenomena have been used for designing different kind of optical devices, starting from lensing, super lensing, etc. Antenna engineers and RF engineers are using for other kind of applications. So with this, a very brief introduction of the metamaterial, because the structures that I'm going to discuss are basically metamaterial inspired structures, even though those are not metamaterials. At the very outset, I just encourage all of you, because I'm going to cover a lot, many things I'll be probably a little bit probably fast, and I won't get the enough opportunity to explain many concepts in very detailed manner. That's why I advise you to go into these papers: antenna advance for cognitive radio, a dual reconcilable printed antenna. These are the first author of the first paper is my PhD student Latif Shaikh, who after graduation is now working at Space Application Center Ahmedabad as scientist. And then the second paper I'll be going into the details of these two is a dual reconfigurable printed antenna. Here also, it is outcome of some BTech and PhD students research, and the many other work that I'll be discussing in this presentation are finally culminated in a book by us, and that book is Multifunctional Ultra-Wideband Antennas, Trend Techniques and Applications, authored by myself, Professor Siddiqui, and Professor Yahya Antar, my Canadian collaborator. So because I'll be using the splitting resonators very often in different kind of structures, I thought giving you a very brief info about the splitting resonators. So these are three different possible structures: the circular, the square, and hexagonal type of structures. So we have extensively calculated the resonance frequency of this structure. We have proposed a new and better modified structures resonance frequency calculation. So this is the typical equivalent circuit proposed by Ricardo Marcus, the Spanish group, and in 2011 we proposed a modified equivalent circuit which gives more accurate results, because these are very narrow band resonators. So precise calculation of resonance frequency is very, very important. So these are some of the expressions which are used, closed form expressions for calculation of the resonance frequency for this kind of structures. At our institutes for the MTech level, I offer one course, one elective course on metamaterial inspired antennas. Just a minute. So there I take almost 40 lectures for this course. So you can understand, the course covers many things, starting from circuit aspects to antenna aspects and other kind of applications. So there actually I explain all these things in a more detailed manner. But here because I'll be going into the main agenda of this presentation, so I advise you, those who are new, especially for them, you can go into some of our articles and the book chapters where you'll be getting the details of this particular theory. So this is the resonance frequency for three different kind of structures: the circular, square, and hexagonal type of structures. This is based on calculation of the inductance and capacitance. So these inductance and capacitance is calculated in different fashion. And one new other concept that we introduced is the orientational change of the inner ring. So in the conventional structures, the outer ring gap and the inner ring gap lies on the same axis. But in this case, deliberately, the gap of the inner ring is rotated to change its resonance frequency. I'll be explaining this phenomenon later on. And when you calculate the capacitance, which is basically distributed capacitance, so you have to calculate in terms of the per unit length capacitance. So that's per unit length capacitance can be calculated in this fashion, and the inductance can be calculated using the closed form expressions, and then depending on the three different geometry, whether you have a circular or a square and hexagon, you can basically use a different values of constant gamma, and this is basically closed form expressions from Turner. So because many researchers used to write us that they are trying to calculate the resonance frequency of splitting resonators for different applications, but they are not sometimes getting the proper results. So we thought of we used to respond to all the authors, but we in a later communication we thought we'll keep a small part in the appendix where the computation of the resonance frequency will be made completely clear. So this is the appendix section of our recent paper, which got published in 2018, IEEE Transactions on Antennas and Propagation, volume 66. You can see over here. So for a particular SRR size of given external dimension, C dimension, D dimension, and G dimensions, and given substrate parameters, we have shown in a step-by-step fashion what is the resonance frequency. And for the given dimension I talked about, the resonance frequency is 4.13 10 to the power 9 gigahertz. So once this paper was published, and then probably people can definitely check by step, and there will be no chance of any mistake or any confusion. So then this was, we did it deliberately to help the community, because we are having our code, and it's a simple code only, but the process of the modification was more important. But this was quite useful. So these are some kind of, I was talking about different kind of resonators, but those resonators, if you actually print on a laminate, a dielectric laminate, it looks like this. So as you can see, this is the square, circular structure, this is square structure, this is offset square structure, this is hexagonal structure on 3M material, and this is the back side because these are loaded on a coplanar waveguide type of structure. So you have the ground planes here, and you have the intermediate signal line there. So now we come to the different kind of applications. When it come to the applications, we worked on the antenna applications, we worked on different kind of filter applications, wideband and multiband notched filter and very wideband rejection. So these are some different kind of structures, and the final application, which was a breakthrough, was to apply these metamaterial kind of structures, the resonators, on a CPW fed dipole antenna, which many people call them filtena, many people call them metamaterial antenna or whatever, but we call them metamaterial inspired antenna. And these pair of the resonators are actually loaded just beneath this section of this CPW line, which I'll be explaining gives a unique response of that antenna. And later on, that unique antenna was further modified to come up with multifunctional antenna, where the same antenna can work for different kind of applications. So before I go into that, this is probably the last slide on the application side. Like these are, as you can see, you have different kind of resonators. In fact, I remember some of these structures are fabricated at Dr. Pandey's lab, Dr. B.C. Pandey's lab at LRD Bangalore. He was the director technical at that time. And as you can see, these kind of splitting resonators in an arrayed configuration were loaded on the CPW line. So each of them are having different kind of orientation and small subtle change of the parameters, and thereby you get multiple resonances, which gives a very beautiful, strong notch applications. And then for theoretical understanding and to ensure that your results are correct from all aspects, because you can do EM simulation, you can do some kind of calculation which I was showing in previous slides, but another way to verify them is to involve some kind of circuit simulation. So for doing that, you need to understand what is the equivalent circuit of this overall CPW fed line with these SRR loading. So if you take half of the section because of the PNC condition or the magnetic symmetry condition, so you can just apply half, take half of the section, and you replace the CPW line by its equivalent circuit, and then you apply these the impedances at the 2R0 at the output match termination and input match termination also 2R0, and those resonators which are loaded to two different orientations are replaced by their equivalent circuit. And how the resonators are linked? Because resonators are coupled by the CPW line. So it is the field of the CPW line which excites the resonator. So if you replace them by the coefficient of coupling here and there, then you get the full picture. So this is the realized prototype of the notch filter, and then these are some of the results, as you can see over here, for dual frequency rejection for two different applications, like for one case, and this is the other case, which is basically for a very wide band rejection. As you can see, the measured rejection band is below minus 40 dB in some frequency band with a minimum rejection of minus 30 dB. And these are different kind of extensions of the work, because I am saying these structures have been further loaded on different kind of antennas. So I'll be going into the details of this, like how these antennas are loaded on a Vivaldi antenna. As you know, this is a Vivaldi antenna, and this is excited by this microstrip line, and this microstrip is converted into radial stub over here. So is the slot on the back side, right? And this ensures a good wideband matching, and these resonators are loaded over here. And this is a modified Vivaldi kind of structure, where the slot was actually intentionally bifurcated into two different structures. So this work was reported, and I guess we presented in Montreal in 2015 or 16. So two different kind of structures are loaded over here. This is same kind of concept used on a dielectric resonator antenna, and this is on a horn antenna. So these are the application side of the as I'll be showing now that this loading on different kind of antennas has great implication in terms of the multifunctional antennas, in terms of cognitive radio antennas, and now I'll be showing very soon that how some of these near field resonant particles, when loaded suitably on an antenna, can not only give the notches, it can give some other kind of antenna performance also. When I say other kind of antenna performance means I'll be showing a recent work reported by us in using this type of resonators for reducing the mutual coupling in the MIMO antennas, and also using them as a electrically small radiator for 5G applications. So this is the uniqueness of our concept and our idea, because it is radiator independent. And because it is radiator independent, as you can see in this particular case here, this resonator is loaded on the feed region. And this is a microstrip feed, and this particular bottom part is actually the ground, this orange color, and this little bit what can I say? This is also brown color, probably little bit faded brown color. So this is on top, which is a microstrip, and this part is the ground. This part gets tapered, and finally it takes a shape like this. So this is the bottom metallization, and this is the top metallization. This is an excellent antenna, and this is called antipodal tapered slot antenna. It is tapered slot antenna but the two metallization are on two different sides of the substrate, so we call it antipodal. So in antipodal kind of structure, with two different orientation of the rings, one here and another here, you actually design beautiful frequency notched antennas. Reported, as we have reported in IEEE TAP and ATAL 2017 and 2018 respectively, you'll see if you go into the details of the paper that this structural orientation and these two different kind of loading is very strong, very strong notch frequencies. So with this lot of applications I showed in the circuit side as well as the antenna side, I'll show how some of these metamaterial kind of structures when loaded in a substrate in some other way to excite the resonances, and you can actually even apply them for designing some very short electrically small antenna for 5G applications. So not only the metamaterial concept but other concepts also I'll be going to show. So this is the second part of my presentation. Just a minute. So this is recent design of different kind of 5G antennas. This is a slide which was recently presented by one of my students at 5G World Forum virtual conference in 2020. It happened in just few years before in Bangalore. As you know that IEEE Future Directions Initiative, that is the 5G initiative, is coming up with this conference, and this was a very prestigious forum because there were industry leaders, there were of course the academic presenters, but this conference is mainly dominated by industry. So there we proposed our work. But before I present our work on some of the 5G antennas, I'll be talking on the base station as well as the mobile equipment kind of antennas. And our future plan is to take this kind of structure for massive MIMO kind of applications. But before we go into that, you know probably that this evolution from 1G to 5G, and this evolution is in all fronts, from bandwidth to frequency of operation and etc. So if you see the basic features and why we are going for these new bands or new features, etc., needless to say, you need not be an engineer to understand that it is basically communication drives and requirement in multiple fronts that takes us through this innovation. So for 1G, it was basically the analog signals that based on AMPS, and it was typically using the frequency division multiplexing. It is then there is 2G where it is based on GSM, and then GPRS that global position radio switch, etc., age, etc. was used. Then 3G you have achieved up to higher data rate 2 Mbps and all. But then when it comes to 4G and 5G, it was the long-term evolution based on LTE, much higher data speed, and here the main thing is aimed for IoT, VR, AR, cloud computing, etc. And this is using the massive MIMO systems. And the cognitive radio, which will be the last part of my talk, is also another enabling technology to ensure better spectral efficiency. So I will connect this second part of my presentation and third part of my presentation through our work. So before I go into the work part, so let me also show, this is a slide which is actually based on one of our chapters in our book where we are talking about the very fundamental ideas regarding the MIMOs. If you have a single antenna at the transmitter and receiver side, you call it a single input, single output, which is, you can say, SISO. And this is multiple input at the transmitting and multiple input at the receiver side. So it will have obviously the path diversity, then different kind of other diversity, pattern diversity, polarization diversity, all these things you can talk about. But then the main feature is you have multiple antennas at the transmitter and receiver side. But if you have either multiple antennas only at the transmitter side or only at the receiver side, you can theoretically talk about another two configurations, which is SISO to MIMO, then SIMO and MISO. So single input, multiple output, multiple input, single output, multiple input, multiple output systems. So the basic idea is basically when you have, you talk about the channel capacity, for a isotropic kind of system. So this is the channel capacity for a given signal to noise ratio, depending on the number of users at the transmitter and receiver side. And if you have more directive antenna, the channel capacity is increased by the gain of the transmitting and the receiving antennas. And so this is in bits per second per hertz. So one of the mechanisms is to have more bandwidth, then obviously you can increase the channel capacity. Another concept is to have higher gain, that is GT and GR is more. But the other point is, if you have more number of antennas, like if you have M antennas here and N number of antennas here, the channel capacity is increased by M types or N times, whatever be the lower. So if I have 8 antennas at the transmitter side, 8 antennas at the receiver side, we will get channel capacity increased by that many number of times as you have the number of antennas. And this is automatic extension of the point that I discussed, that is multipath and diversity. So you have a multipath scenario over here. As you can see, you have a transmitter and you have a receiver. And what happens is, in our environment is dynamic. So that means you have multiple type of scatterers. If you think in a real-time situation, you have multiple buildings in an urban environment, you have more number of buildings, you have different kind of scatterers. Some of the scatterers are moving also. So then definitely it is from transmitter side to receiver side, you might have a direct path, but then you have many more number of paths which are coming through different kind of fading and different kind of multipath effect. So the problem is when you have a given path, you are not sure whether you receive the optimum data or not. But if you have multiple number of paths, depending on the different kind of phase differences that can happen with different kind of paths, you can actually ensure that at least one of the paths will not be lost and you will get a good amount of data. So this is the advantage of the multipath kind of situation, but this is, I am telling in a very simple way, but lot of signal processing and lot of other electronics has to be involved to ensure that you choose the proper path. And then this is an example of a 2x1 receive diversity system. As you can see, you have a 2x1, I am saying because you have the 2 number of antennas at the receiver side and 1 number of antenna at the transmitter side. You just consider the 2 number of scatterers. So this you have a path 1 like this, then you have path 2, and then you have a path 3, path 4. I mean, if you consider such situation, you will get a real-time idea regarding the total number of paths. And as you are in a massive MIMO, people are talking about many more number of antennas, so you can understand that the channel diversity or the reception diversity will be much more. So these type of applications are being considered, and this is the part before I enter into the work part. I just wanted to show the requirement as far as the current technology is concerned, the 4G is concerned, and the upcoming 5G technology. So it is not only all about the spectrum change. Some people are thinking that 5G means we'll be moving to at a very high frequency range and we get a huge bandwidth. It is not exactly that. So you have to understand what is the current and the future vis-a-vis. So In terms of the antenna length, frequency range, maximum urban transmission range, signal attenuation, because obviously you have different options, but one of the options is to move at the millimeter wave range. So if you go to the millimeter wave 5G range, like 28 gigahertz or 38 gigahertz, and some of the countries are talking about 60 gigahertz also, then attenuation will be pretty high. So then you have to have a very high gain antennas also. Then what is the average user data rate? The current technology, how much is supported, and how much we are aiming for millimeter wave technologies, the upcoming technologies. So all these things we have to place side by side, then we get a better idea, and then we get a better idea in the sense we have an idea like what we are aiming for, and then only we can come up with a proper design. So this is the 5G motivational and challenges. Consumer device bandwidth requirement is increasing, and 4G and 5 3G bands below 3 gigahertz increasingly crowded. So push for 28 gigahertz frequency. Initially, it was thought like that the we will be covering at moving at to a very high range, and then attenuation being high, we have to have a very high gain antennas. But as I will be showing in the next slide, like if you see the different frequency bands which are being conceived for upcoming 5G applications, it is not only just the this millimeter wave bands, so 28 or 38 gigahertz or 60 gigahertz, but lower frequency bands are also being considered. So sub 1 gigahertz band, which is like 600 megahertz and 700 megahertz, objective is wide area coverage. Sub 6 gigahertz band, we are working in this area, as I will be showing very soon, 3 to 500 megahertz bandwidth over here, 3.3 to 3.8 gig, and then you have around 403 megahertz or around another 500 gig over here. Like these are sub 6 gigahertz, that is below 6 gigahertz. So these are different governments, different localities, local government, and different countries are conceiving. But definitely one attempt is there to move towards the millimeter wave band. But there will be more challenging. Not all the academicians and researchers can work, because as you move below above 30 gigahertz and above 40 gigahertz, your facility becomes costlier. So you need a better fab facility. You need to have a, of course, better costly network analyzer and costly other equipment for doing the measurement. Anyway, so if you see the entire picture with a holistic view, then you have these are the different kind of combinations available with sub 1 gig, sub 6 gig, and sub millimeter gig, millimeter wave frequency range. And these are some of the antennas. If you do the literature survey for
Sir, just not audible, sir. Sir, you are muted, sir.
muted. Is it okay now?
Yes, sir. Yes, sir. Only the last.
I think Google, okay, I think it is Google back probably, because once I go to the full screen mode, I am not doing anything. Anyway, so you see the slide now? Hello?
Yes, sir.
You can hear me as well, right?
Yes, sir.
So I was talking about some kind of structure. This is for base station kind of application. As you know, the beamforming and all is going to be very important. But at the same time, if you see the back end electronics, it involves a lot of other mechanisms. It may be different kind of phase array network or different kind of other concepts like analog or digital beamforming technique. So this is basically ultimately to ensure you have a very highly focused beam, and at the same time you are having the full azimuthal coverage. So multiple of these type of structures will be loaded in the azimuthal configuration to cover the wider angle, and then in the full azimuthal angle, because as a base station you have to ensure that you radiate in all directions, but at the same time you want a very highly focused beam. So you have a beam which is focused, but then beam is moving in all possible directions to cover the entire kind of azimuth. And these are some kind of arrangements which have been proposed for the user equipment applications, the integrated 4G and 5G MIMO antennas for 3 GHz band. As you can see that considering a typical mobile and considering the display area, he proposed some kind of structures, multiple antennas loaded in different areas for uh, user equipment applications. And coming to the more of the base station applications, like different kind of antennas, starting from different kind of Vivaldi to different kind of even microstrip can work also, because when you are talking about the sub 3 gigahertz and the bandwidth requirement is not high, you have can have multiple microstrip type of arrays, and you can put it in a circumferential arrangement like this. So as you can see over here, you have multiple antennas, but it is little bit of structural engineering. The way you have placed them along a cylinder, a hexahedral cylinder or some other kind of cylinder, you basically ensure their individual antennas are very high gain, and you can have achieve different kind of polarization also, and then you are catering to different user equipment. So these are indicating different user equipment starting from 1 to as many as multiple users are there, and this is the arrangement for your base station antenna. So each of them are covering both horizontal and vertical polarization. So this was some kind of basic literature survey for 5G. If you go into the literature, you will see many more papers, because I want to talk on some of the works that we have contributed, because from there probably you can get some impetus and some ideas in future. And this work we are also doing. As I mentioned, this is a result recently proposed and presented in IEEE 5G World Forum 2020. It is still not available in IEEE Explore because it will take some time. And further work on this direction is in a pipeline for reporting it in other places. So this is basically one kind of structure which is a step impedance resonator, SIR. And you see the red one is basically a monopole. And this monopole is a microstrip, basically microstrip line with 50 ohm impedance, and this part is the ground plane. And this monopole actually excites these two resonators. One is beneath the substrate, and another is placed above a superstrate. So this red part, the cross view or side view, if you see, this is indicating the monopole, and these are the two. This is part is the substrate, and this part of is the superstrate. So here you have basically the superstrate is exciting one resonance, and the substrate is exciting this. So two SIRs. We designed these SIRs so that we covered both 28 gigahertz and 30 gigahertz. With this mindset, with some theoretical calculation, of course, we came up with a design like this. So if you see the results over here, this is the only monopole kind of structure, and then you have monopole with SRR, with bottom SRR over here. You have a structure. So with only monopole, you are getting a resonance somewhere here. When you have a monopole and this SIR, this near full resonator, step impedance resonator, monopole actually excites this particular resonator. And now you see it is 30 gigahertz closely. And then this one, which is second one, the smaller one, which is loaded on the superstrate, this part is indicating the superstrate. And this gives close to around 32 gigahertz. But when they are combined, like these two top and bottom SRR is combined, the monopole excites both of them, and you get one resonance almost at 28 gigahertz and almost at 30 gigahertz. Some optimization is done because of the proximity coupling, and because of mutual coupling, there will be some shift when you place both of them identically. So if you initially design for 28 and 38 gigahertz, then you won't get at that frequencies when you consider their combined operation. So little bit of innovation and engineering ideas you have to apply. So as you can see from this surface current distribution, at 28 gigahertz, the bottom SRR, which is little bit larger, is excited, whereas at 38 gigahertz, the top SRR, which is a little bit smaller in size, is excited. So that was the first piece of work. And the second piece of work, because as I said, we want to gradually take it for a massive MIMO configuration. And because it is at a very high frequency, the devices are very small. So this is a two element MIMO. In the sense, you have just two elements placed side by side with a tiny separation of 2.92 millimeter. And after this configuration, you have to see, because now you are saying it is a MIMO, so you have to see the antenna matching, which is SII, and also you have to see the mutual coupling, which is SIJ. That means S11 and S22. I mean, that is typically should be same, because both the elements are same. But then you have to see the S21 also. So when you see this blue one is actually indicating the S11 good matching at 28 gig as well as 38 gig with reasonable amount of bandwidth that is needed for 5G bands. And also the S21, which is indicated by this red one, is pretty good because we have not used any kind of isolation enhancement technique. Literature, people have used different kind of isolation enhancement technique, but in using them and incorporating them at millimeter wave always might not be very straightforward and easy. So if we can achieve this optimum mutual less mutual coupling with good amount of isolation without using any other kind of structures, that would be good. So for as far as our application was concerned, this was pretty good. And as you can see, we calculated the ECC using the conventional S parameters technique, and also later on based on the radiation parameters, like where the directional nature of the antenna is also considered. But for most of the environment, this S11 parameter or S parameter based extraction is good. So and this is the envelope correlation coefficient. As you can see, at both the frequencies of the antenna 28 gig and 38 gig, that ECC is pretty low. Along with that, other parameters that we see like TARC, TARC, total active reflection coefficient, and then few other parameters like diversity gain, etc. are also considered. So this is the typical gain of the structure at 28 gig and 30 gig, because you are saying it is a two-port MIMO. So you have to see the pattern diversity also. That means when you excite these antenna, keeping these as match terminated, and also excite these antenna, keeping these as the match terminated. So the idea is, if you have multiple antennas, suppose rotating in this kind of fashion, and then if you can tilt the beam in different directions, that would be very useful, as I was explaining in the previous configuration. So this is the situation when port 1 is excited and port 2 is match terminated. And this is the situation when it is just the opposite one, port 2 is excited and port 1 is match terminated. And then this particular concept was extended for 4-element system. So I will show those results very fast. So these are the same configuration, but now you see 1, 2, 3, 4. There are 4 antennas and they have a vertical as well as horizontal separation, 2.92 millimeter, and you see the entire overall size of this structure is only 7 millimeter by 6.64 millimeter. So how tiny it is, and then we will be using them as just one structure, and many such structures will be placed together to cover the full azimuth and cover some of the other applications. So all parameters are kept and single element design. Even with this 4-element design, we see similar kind of performance. 28 gig, 4 gigahertz is the bandwidth, and at 38 gigahertz also around 1.2 gigahertz bandwidth is achieved. ECC is pretty good for both the bands, as you can see over here, row E, 1, 2, 1, 3, and O4, because you have now multiple antennas. So if you have ECC from port 1, then you have to see at 2, at 3, and 4, and so on and so forth. So for all such combination, the result was pretty encouraging. And this is the pattern diversity when you excite the port 1, then excite the port 2, excite the port 3, and excite the port 4 combined. So as you can see, direction beam maxima is changing depending on which port you are actually exciting. So this is pretty encouraging, because you need to have similar kind of design when you talk about the full coverage in a real-time situation. So this is the same thing, but at a different frequency, because we are saying that our antenna is working at 28 gig and 38 gig. So the first one was for 28 gig and this one is for the 30 gig. So for more information regarding this work and this paper, you may see this article, Design of NFRP based SIR loaded 2-element MIMO antenna system for 28 and 30 gigahertz sub-millimeter wave 5G applications, authored by my MTech student and Dr. Sarkar, Professor Siddiqui, and Dr. Ganguly, and Dr. Yahya Antar from Royal Military College of Canada. This paper is not immediately available at IEEE Explore, but because 5G World Forum happened in a virtual podium, so those presentations, even the video presentations, are uploaded in their website, and I know that those are made available to the people, not only the participants, but the global people also, without any financial implication. So you can go and see some of those results from them by loading our presentations. Just one more minute. So before I go to the last leg of my presentation, which will be the cognitive radio, so I'll probably there is a small break, right, after some time.
Yes, sir.
Hello. Yeah. So do you have a small break in between, as per the schedule, or you want me to continue?
Yes, sir. 15 minutes break.
15 minutes.
Yes, sir.
Okay. So now I'll continue, and because before the cognitive radio part, I'll stop. At that time, we can have a small break so that I can also have a cup of tea here. Okay.
Yeah, fine, sir.
Yeah. So this is I was talking about the base station applications. Now I'll be talking about some sub-6 gigahertz frequencies, antenna design for sub-6 gigahertz, which is for user equipment applications. As you can see here, there are two kind of set. One is the vertically oriented. These are all slot type of radios, and these slots are being excited by this type of arrangement. These are basically the 50 ohm line, and this point, the red point, is actually the excitation point. It comes like this, and it excites the monopole, and that monopole excites this. The microstrip excites this slot. And as you can see, the detailed dimension over here is given. We have placed their location in a way such that the other electronics of the handset positions are not impacted. So these are all in millimeters. The dimensions of each of the thing you can see. Some of the things are very, very fine. So there are 8 antennas over here. So we call them A1 to A8. So these 8 antennas are placed for sub-6 gigahertz application. So it is a 8 element MIMO antenna, you can see. And as you can see from S11 to S88, the antennas are giving very good responses for both the bands around 3.5 gigahertz and around 5.5 gigahertz, which are the two possible bands for sub-6 gigahertz. In fact, in India, initially we are not thinking about the millimeter wave 5G band. So the first configuration that Vodafone and is already in pipeline, they are talking about the sub-6 gigahertz band only. But in this work, I'll show later on that how we combine sub-6 gigahertz and millimeter wave 5G band together. So this is the other results. As I said, we have to see the mutual coupling, that is S1 to S, in general I can say Sij, and for all combinations, when we are seeing the isolation between two adjacent elements, that might not be very good, like, but still it is acceptable because it is below minus 10 dB. But some of the elements which are widely apart, obviously their isolation is I mean pretty strong, like coupling is very less. For example, you see all of this, I mean these onwards, the blue, the um, sea blue onwards, all are pretty good below minus 30 dB, minus 25 dB. Only for one case, the two antennas are pretty close to each other. That too at some frequency it is going to minus 10 dB, but that is also acceptable range. So this is the typical pattern 3D polar plot at the two frequencies 3.5 gig and 5.5 gig. And as I said, that we want to have another arrangement for millimeter wave band. So this is the another arrangement of the antenna. Here also we have 8 elements. If you see the position of the previous antenna, we have used it over here and here. And here along the rim of the cell phone, as you have seen typically at the rim, like in this region and in this region, the antennas are typically placed. So here another 8 antennas, A1 to A4 and then A5, A6, A7. Another 8 antennas are placed in this fashion. And this is supported by Taconic TLOI3 substrate. And this is basically a branched type of monopole. And each of the element will be covering two frequencies because these length and these length are made purposefully different so that you get one frequency around 28 gig and another frequency at 38 gig. Okay. So then in the next work, I will show you how we have combined these two designs. So here, this is the millimeter wave band, 8 elements, and earlier I was talking about another 8 elements which are placed at the periphery. The mechanism is different because this is 28, 38 gig, these are much smaller. And as you can see from the scale diagram, these looking very, very small when you see compared to them. So these are the sub-6 gigahertz 8 elements at these microstrip excited slot type of antenna. And these are the 28 and 38 gigahertz millimeter wave band. So these two operations or these two structures are combined together. And another important parameter, even though I did not tell you like how the isolation uh, it can be enhanced. Like for our design, it is really hard to apply any other isolation enhancement technique over there because the antennas are so small and so closely associated with each other at proximity. So it's very wise to use those isolation enhancement technique always. But in some cases, for some other applications, you really want a very good amount of isolation. So there, people are using different kind of isolation enhancement technique, like neutralization line, different kind of resonators, splitting resonators also sometimes. Then CSRR, different kind of defecting, and ensuring the current undesired current doesn't reach from one antenna to another antenna. Here we proposed one kind of mechanism which is a high isolation MIMO antenna for cognitive radio type of applications. So you have two type of antennas is there. One is wideband monopole, which is ultra wideband, and a narrowband antenna. To enhance the isolation between these two antenna elements, we have actually placed some kind of multiple EBG type of structures. This dimension of the EBG of structures are obtained from this phase plot. So as you can see, the reflection phase 0 indicates the resonance frequency. So these EBG1 to EBG5, you have 1, 2, 3, 4, 5 resonance frequencies. And these 5 resonance frequencies are contributed by different elements which are loaded between these antenna 1 and 2. So the largest one will be corresponding to the lowest resonance frequency, and the smallest one will be corresponding to the highest resonance frequency. As you can see, these antenna elements are already integrated inside the anechoic chamber. These are coax cable and all. There are a lot of additional precautions that you have to take when you place this type of antennas inside the chamber. So using these mechanisms, using the surface current distribution also with and without the EVG, you can probably realize that when we don't have the EVG, the two antennas are quite coupled, whereas when we place these kind of structures, the coupling is very less. So this is the measured results. As you can see from this VNA screenshot also, the top brown line is actually indicating the S11 response of the wideband antenna. As you can see, the S11 is below -10 dB for a large wide ray frequency range from 2 to 11 dB, whereas S21, which is this blue line, which is in the bottom side, is pretty high for the entire band. It is below -25 dB for the entire band, excepting a small frequency range here, which here also it is below -20 dB. So this is a very good arrangement for isolation enhancement. At the same time, as you can see from the simulated and measured response, so because the two antennas are coupled together, there is some kind of impact, and therefore the radiation pattern is also a little bit tilted. It is acting like an Yagi kind of concept. So this antenna is a without any other antenna or other structure, it is a perfect monopole. So you'll get null along this direction, and you will have typical maxima and 45 degree with along the axis of this. But then because of the presence of this one, the beam is little bit reflected, or beam is little bit tilted. So that's why you see this part is like half of the height, but this part is not perfect half of the height. So this is because of the Yagi kind of effect. And same thing you see at the H plane also. So perfect monopole, these will look like a circle. But in this case, you see this half is like a half circle, and this part is like as if something has pushed it. So similar kind of phenomenon you see a Yagi kind of structure. So let us take the break and then go back to the last part of the presentation, which will be antenna